There Might Be Hope, Chapter 6, The Diversified Farmer. Now Abel was a keeper of the flocks, but Cain was a tiller of the ground. Genesis 2:2. The origins of farming and ranching are as old as Cain and Abel. Farmers, traditionally, stayed rooted on a single parcel of land, using a few animals for their strength and manure to grow crops. Ranchers, herdsmen, or shepherds moved seasonally from one grazing area to another to allow their livestock to convert natural forage into meat and fiber. Capable farmers thoughtfully applied their manures back as fertilizers. Wise ranchers kept their pastures from being overgrazed. A natural cycle and rhythm to life existed within the bounds of each endeavor. Following the Civil War, northern states and even England were hungry for beef and had the money to pay for it. Texas had an abundance of feral cattle and grass. Emerging railways offered entrepreneurial opportunity for those willing to risk their lives driving the cattle on horseback from Texas to Kansas. A roughly 3-month trip, trails were fraught with danger, but the lure was being paid immediately upon depositing the cattle in cash. Cowboys earned a living, chuck wagon cooks got ahead, and trail bosses got rich. Along the way north, cattle grazed steadily as they ambled along. Once they arrived at a railhead, they would be shipped by rail car to the Chicago Union stockyards. If Texas in the 19th century was a sea of grass, Chicago was moated by an abundance of corn. Once at the stockyards, these feral cattle that had just walked from Texas to Kansas would spend their last 100 days in dusty wooden holding pens, being fattened on corn at Packingtown on the edge of the Chicago stockyards. Not only were butchers able to increase their profit by adding pounds to their final product, but the corn gave the beef a comparatively mild and unique flavor to that of grass-fed beef, which had been the previous standard. Prior to the advent of the Chicago stockyards, it's important to remember that butchering a steer was often intensely personal. Families and small landowners either butchered animals they had raised themselves or personally delivered them to a local butcher. Calves were likely to have been cared for and lovingly watched over. Children often played with them and doted on them. Not only personal, butchering a steer was also an intensely physical, all-day task, easily requiring 8 to 10 hours to complete. After slitting the throat, a butcher needed to hoist the roughly 1,000-pound carcass into the air and then carefully remove its swollen and bacterial-laden intestinal tract from the body without puncturing it or contaminating the meat. Next, a butcher leveraged his body weight using his bare knuckles to alternatively pull and fist or push the hide down to separate it from the animal's body. Finally, he must saw through bone, muscle, fat, and tendon, tediously breaking down the carcass, piece by piece. There was nothing personal about the Chicago slaughterhouse. By leveraging the power of the assembly line, they could process an entire steer in 35 minutes. A model of efficiency, they moved up to 2,500 steers a day through their facilities. Corn-fed beef that had originated on the wild Texas plains would then be shipped in refrigerated rail cars to restaurants and groceries on the increasingly urban eastern seaboard. From 1890 to 1930, Chicago supplied up to 80% of America's beef. The invention of barbed wire gradually diminished the open range and herds of wild cattle. The cattle trails were replaced with more railroads, and then the highway replaced the railway. The Chicago Union stockyards in Packingtown shut down, but the slaughterhouse assembly line model was here to stay. America had fallen in love with corn-fed beef. So the slaughterhouses followed the corn and migrated to the Midwestern grain belt to save money on shipping feed. Further and further, technology and mechanization separated American citizens from what had once been an intimate connection with their food. It wasn't just the beef industry that saw dramatic changes during the 20th century. Lamb, which had once been a staple of American diets, became unfashionable following World War I. Returning GIs had eaten their fill of cold, greasy, canned English mutton war rations. Meanwhile, a pig and some chickens had once been backyard American staples for every household. As Americans moved to the suburbs, they left behind their pigs and chickens. Swine and poultry farms became increasingly consolidated and themselves moved from outdoors to indoors within massive climate-controlled buildings on concrete and plastic floors. Laboratory-like and fastidious, these houses maximize sanitation and minimize disease. They also cut swine and poultry off from diet that had, for millennia, held an intimate relationship with the soil. In fact, baby piglets that once naturally received essential iron by snarfling in the soil had to start receiving iron injections once they began to be birthed on concrete. Last of all were the dairies. Even into the 1980s, most communities, even small towns, had at least one local family dairy that provided milk to the community. A large dairy might have had 100 cows that grazed on rolling grassy pasture lands. Then in the 80s and 90s, increasing government regulations crippled and shut down countless local family dairy farms, opening the door for increasing industrial consolidation on a massive scale. Like the beef feedlots, dairies became regional operations, often with thousands of tens to thousands of dairy cattle housed in relatively small barren pens. Collectively, these new livestock management models became known as confined animal feeding operations, or CAFOs. Relative to dairy cattle, beef cattle don't stay in CAFOs very long. Some may have grazed on residual crops in farm fields prior to entering a feedlot, but they spend most of their lives on grasslands that haven't been chemically treated. Lambs are also raised mainly on rangeland and then spend their final days in a feedlot. Swine spend their entire lives on concrete or plastic floors eating grains, as do chickens. Most of these animals are terminal, meaning they will not reproduce or pass on their genetics. They live relatively short lives, usually less than 18 months, and serve their purpose of feeding others. There simply isn't much time for pesticides to accumulate in the bodies of terminal livestock. Pesticides have what's called a half-life, or the amount of pesticide the body excretes through the urine within 24 hours after consuming it. The rest of the pesticide may be excreted later, unless the liver and kidneys are too overburdened. In this case, they will be stored in the body. Most American beef, lamb, and swine simply aren't alive long enough to accumulate a significant amount of pesticides within their body in a single generation. Dairy and egg production are another story. Laying hens, when they're producing optimally, are kept for 2 to 3 years. Dairy cattle are the longest lived of all commercial food animals. A dairy cow's optimal productive lifespan averages around 5 years before they are retired or butchered. Unlike beef cattle, which are usually only fed a concentrated grain diet in the last few months of their lives, dairy cattle and laying hens are fed a concentrated grain diet most, if not all of their lives. In America, dairy cattle, unless grain-fed, are fed a diet consisting mostly of soybeans and corn, often supplemented with ground, dry blood, or fish meal. Sometimes this may be supplemented with cottonseed meal or soybean hulls. In 2020, 94% of all soybeans were genetically modified, and 92% of corn planted was also genetically modified. Almost 93% of American cotton is also genetically modified. It's a diet of convenience and economy. Externally, this diet does not seem to have any ill effects on its immediate consumers. But globally, cattle cancer rates have been on the rise for the past 15 to 20 years, roughly the same amount of time since GMO feed became the norm. Is it possible that we don't have quite as much control over agrobacterium as we would like to believe? When agrochemical companies defended their products from the 1950s into the early 2000s, much of what they had to say wasn't necessarily dishonest in regards to the chemical safety. Much of the time, these companies honestly and candidly didn't understand the mechanisms and actions behind their chemicals. Besides, the stakes were lower. When chemical pesticides were first introduced, still relatively pristine environments could absorb poisonous halogens and other sites and pass them down the line to less saturated environments. There was always a less concentrated environment to spread these chemicals out on. Ecosystems are wonderfully designed with all sorts of contingency plans and an amazing ability to restore their own health. What a farm, soil, animal, or man ingests isn't what makes them sick so much as what they can't eliminate. By the early 1970s, an EPA study showed agricultural chemical contamination not in some American waterways. They found agricultural chemicals in every waterway in America, every river, every stream, every one. We know the effect these agricultural chemicals have on insects and plants. But how do they affect livestock if they accumulate, if at all? About 700 different active pesticides are currently in use. These include insecticides, herbicides, and fungicides. Sides are grouped by their method of killing, and there are two primary classes or methods by which sides in agriculture kill. The first class of sides poisons living systems. Usually insecticides, this class impairs or altogether stops vital processes within insects. However, they are not species specific, only dosage specific. Scientists candidly and frequently admit that they don't fully understand how these chemicals work, but we do know they work primarily to disrupt an individual's nervous system, metabolism, digestion, and or reproductive system. About 85% of insecticides focus on disrupting or shutting down nervous and muscular systems. These are the acetylcholine inhibitors. Acetylcholine is the Paul Revere of the body. All throughout mammalian bodies, there are receptors for acetylcholine to relay its essential messages. Acetylcholine tells the animal's lungs to breathe, its heart to beat, and its stomach to digest food. They shout to muscles to run or fight when danger is present. Acetylcholine receptors form a complex relay system throughout the brain and spinal cord, soft tissue glands such as the thyroid, voluntary and involuntary muscles, and bone marrow stem cells. When activated, these receptors enable nerve impulse communication and consequently tell muscles when to move. The vast majority of today's insecticides are irreversible acetylcholine inhibitors. Commonly known as organophosphates, this group of insecticides causes death by overstimulating and exhausting the insect's nervous system. The remaining members of this first class of sides are honed in on stopping or altering insect growth, energy metabolism, and digestive membranes to the extent that the insect either dies or is unable to reproduce. In other words, insects that ingest these insecticides stop growing, are lethargic, can't digest their food, and or become infertile. The second class of sides isn't intended to poison plants. Their lethality lies in their ability to starve the target plant to death by creating nutrient deficiencies within that plant. This second class includes amino acid inhibitors, fatty acid inhibitors, growth inhibitors, cell membrane disruptors, carotenoid disruptors, and shikimate pathway disruptors. The most prominent of the amino acid inhibiting herbicides today is Roundup, but a short list of other modern amino acid inhibiting pesticides might also include the following: Accent, Accord, Amber, Assert, Arsenal, Autumn, Beacon, Cimarron, Classic, Equip, Escort, Express, Everest, First Rate, Glean, Honcho, Matrix, Maverick, Olympus, Option, Oust, Peak, Permit, Plateau, Pursuit, Python, Scepter, Sledgehammer, Resolve, Raptor, Touchdown, and many, many others. While glyphosate stops tryptophan and phenylalanine production, chlorsulfuron, for example, stops the target plant from producing two other essential amino acids, valine and isoleucine. Resistance to these herbicides has reached a level where they're frequently applied as cocktails to enhance their strength. These herbicides not only disrupt amino acid and protein production in their target plants, but also in the soil microbiome by destroying algae and mycorrhizae. With the algae and mycorrhizae diminished or destroyed, fields sprayed with these amino acid disruptors are also most likely producing fewer amino acids for livestock to eat today than they would have 80 years ago. Thus, logically, the nutrient deficiency extends from the target plant and affects plant consumers. Of course, it's impossible to know for sure whether our livestock today are consuming fewer amino acids than livestock did 80 years ago, because we can't turn back time and test soils from 80 years ago, and no otherwise comparable soils exist today. Until quite recently, all livestock diets were based around the concept of crude protein, a grossly oversimplified concept. As long as the crude protein or CP of an animal's feed was high enough, we considered that their protein needs were met. We didn't measure any other nitrogen such as amino acids. Like synthetic and organic nitrogen fertilizers, crude protein was based off the idea that livestock needed a certain percentage of nitrogen in their diets. Now we recognize that livestock, like plants, don't actually absorb nitrogen very well. Their bodies are searching for amino acids and more complex proteins, and they need them in specific ratios to each other. The closer we can achieve the optimal amino acid balance for an animal, the healthier and more productive that animal can become. The next group within the nutrient deficiency herbicides are the fatty acid inhibitors, such as Harness, Keystone, Sure Start, Surpass, Volley, and Warrant. This typically chlorine and fluorine-based group of herbicides stops plants from producing long-chain fatty acids. Fatty acids are basically giant carbon storage bins in the soil, and they're absolutely essential for neurological, reproductive, and digestive health in mammals. Famous fatty acids include omega-3s and omega-6s. Soil nematodes create omega-3s. These are the same nematodes that mycorrhizae capture, dissolve, and send the nutrients back to their plant partner in exchange for complex carbohydrates. Another tiny soil microbiome creature that creates omega-3s are springtails. In good times, mycorrhizae store fatty acids away, both for their own later consumption and also as a means of building soil currency. Healthy soil microbiomes are rich in fatty acids, and we might consider them the foundation to soil health. In fact, some soil scientists are now gauging soil microbiome health by measuring the quantity and diversity of fatty acids within the soil. Like amino acid disrupting herbicides, fatty acid disruptors stop fatty acid production in plants and in the soil microbiome. The next major herbicide group are growth inhibitors. These include 2,4-D, dicamba, and clopyralid. These primarily chlorine and fluoride-based herbicides aim to stop a plant's growth at particular junctures. They may stop seedlings from sprouting or roots from growing. Others stop the growth of stems or prevent plant cells from forming cell walls. Some stop cells from dividing and replicating. Photosynthesis inhibitors as a class, are arguably the most poorly understood of herbicide groups. They were believed to essentially starve plants to death by inhibiting photosynthesis. However, the timeline of the plant's response to these chemicals calls this theory into question. More likely theory is that chemical reactions caused by these herbicides produce free radicals that rapidly damage plants internally beyond repair. Cell membrane disruptor herbicides may actually function similarly to photosynthesis inhibitors in that they promote free radicals in the plant, destroying fat and protein membranes. This highly toxic group of herbicides is often used to desiccate fields prior to vegetable production. Valor, Lotus, Inspire, Action, Aim, and Authority are a few of their trademark names. They have become increasingly popular in recent years due to glyphosate resistance. Pigment inhibitors are often used on rice fields. It is notable that pigment-inhibiting herbicides actually prevent a specific amino acid, tyrosine, from breaking down into vitamin E and creating carotenoids. The plant needs these carotenoids to protect itself against stress. These herbicides also stop the plant from creating chlorophyll. The plant loses both its pigmentation and its ability to feed itself or its mycorrhizae. It dies, and the chemical components disintegrate in the soil or get blown away. A new crop is planted in its place. Most insecticides, herbicides, and fungicides have federally regulated withdrawal times. In theory, these withdrawal times safeguard livestock and people from eating foods with any slide residue. But we know that livestock are receiving trace amounts anyways. Dairy cattle are likely receiving the most. When livestock are exposed to pesticides, they may not have the advantages of generational length and prolificacy that insects do, but they are able to disperse any ingested pesticides over exponentially larger bodies. Their bodies first respond to these dangerous chemicals by, when possible, eliminating them through the liver and kidneys, and subsequently through manure and urine. A pesticide's half-life is the length of time it takes for half of the amount ingested to be eliminated out of the body through manure and urine. Roundup, for example, has a half-life of about 24 hours. The other half of the toxin may be eliminated later, or not at all. Like a busy post office receiving more packages than it has room or personnel to handle, the liver and kidneys can become overwhelmed with more dangerous chemicals than they can eliminate. When these systems become inundated, the body intuitively shunts them away to less essential bodily tissues such as the extremities and bone marrow, followed by hormonal glands made up of soft tissue such as the thyroid and the pituitary. The goal is to prevent these chemicals from damaging essential organs, such as the nervous system and heart. If the body is continuously assaulted by more incoming sides, they will then continue to accumulate in remote and then increasingly vital parts of the body until the liver and kidneys have a low enough load to process and eliminate them, if they ever do. And animals' age and gender also influence how well and how quickly they are able to detox these chemicals. Male cattle are generally better at eliminating Roundup, while females often retain it in their bone, marrow, and soft tissues. Female bodies will eliminate Roundup over time through their placenta into their offspring and through their milk. We can measure pesticides in milk and manure from dairy cattle, but we don't very often. A 2019 study comparing conventional to organic milk pesticide residues was the first of its kind. A well-designed study with a diverse sampling of milk from across the U.S., this study found modern-day pesticide residues in up to 60% of conventional milk samples. DDT and its byproduct DDE were found in almost 100% of milk samples, both organic and conventional. Very few farms in the world have not been affected by these chemicals. DDT is banned within the U.S. but still commonly used in many, if not most, countries globally. Traces of these pesticides show up in dairy cow milk on nearly every continent. In general, our testing abilities for measuring pesticide residue in milk and eggs are quite poor. Scientists are just now researching convenient methods to test for and measure pesticide levels in these products, and most of this testing and measuring is occurring in countries outside of the U.S., such as Europe, the Middle East, Africa, and even China. For decades, American agrochemical companies, along with our research institutions and the FDA, have insisted that bioaccumulation within livestock species was highly unlikely, if at all possible. Thus, how these chemicals may or may not interact with each other outside of their intended insect or plant targets is largely unknown. And while some do not share a common method of action in livestock, most do. In 1989, the Canadian Veterinary Journal recorded a heartbreaking incident of 16 Holstein dairy cattle that were exposed to terbufos, a common acetylcholine inhibitor and organophosphate. The terbufos had been applied to canola seed that was intended to be sown, and the cattle had somehow gotten into it. The signs and symptoms of acute acetylcholine inhibitor poisoning can take up to a week to manifest, and they're fairly unremarkable symptoms, such as diarrhea, colic, and difficulty urinating. These are combined with central nervous system depression. Have you ever asked a cow if she has a headache? Checked her speech for slurring? Asked her what year it was to see if she was having trouble concentrating? This farmer wasn't aware that his cattle had been poisoned until it was too late for 6 of them. Naturally, the cattle couldn't and rightfully shouldn't have entered the food supply, so it was recommended that they be incinerated. Terbufos is commonly used today both as a soil insecticide and a soil nematode insecticide. It's also commonly now found in dog and cat flea repellent collars. It cannot be said enough that acetylcholine inhibitors are not species specific. They're dosage specific. What about lower level acetylcholine inhibitor exposure? What might subclinical symptoms look like? A decline in fertility is usually the most notable long-term subclinical impact. In one study where dairy cattle were exposed to acetylcholine inhibitors, conception rates dropped from 50% to 16%. Progesterone rates also diminished significantly in these females. When a cow fails to conceive, producers typically don't check for potential acetylcholine inhibitor exposure. They find a replacement heifer that hopefully will produce a calf, and that cow goes to the auction barn. Ultimately, her meat may find its way into a family's backyard hamburgers at a kid's pool party or a girls' night out at the local taco joint. We have no reliable pre-pesticide, pre-synthetic inorganic fertilizer, pre-GM control soils to use in scientific studies. Even fields that have been fallowed for the mandatory 7 years needed to be certified as organic can't compare to the fields and soil microbiomes from the mid-19th century or for millennia before that. We do know that insecticides, herbicides, and fungicides have wreaked havoc on our soil microbiome and destroyed both nutrient building and storage mechanisms within the soil. We don't know how much nutrient values have dropped in livestock feed over the past 150 years or so. We do know that nutrient supplementation improves livestock performance. Whether it be amino acid or fatty acid supplementation, every area of dairy cattle production improves with the addition of these nutrients to an already balanced feed ration. Additional amino acid supplementation significantly improves both the volume and the quality of milk a cow produces. It even improves the cow's physical appearance or body condition score. Fatty acid supplementation has been proven to increase female fertility. Cattlemen are transitioning from focusing solely on crude protein to balancing cattle diets for specific amino acids. Animal nutritionists for decades used what we now know were oversimplified feed tags to balance cattle rations. Thus, it is difficult to estimate how different the amounts of complex proteins and fatty acids our soils today are offering our livestock today compared to previous epochs. We also don't know what potential complex proteins may have been built into dairy milk from previous generations with these. While cattle are capable of producing their own amino acids within their digestive tract, they must have adequate building blocks with which to do so. The simple fact is that while we are well familiar with essential amino acids, beyond this, we know that there exists an unknown number of amino acids with which we are unfamiliar, both of their composition and their long-term effects, not merely for survival, but for fulfilling an individual's full genetic abilities. In short, today, we know enough to know there is much we still do not know. The one commonality to all CAFO operations is an abundance of manure, and the question of what to do with it. CAFOs in America produce an estimated 133 million tons of manure each year. The smaller diversified farms and ranches of the past could easily gather their manure and reapply it to their own pastures, fields, or even a family garden. Rich in organic nitrogen and other essential soil nutrients, manure has historically been viewed as an ideal fertilizer. But most CAFOs today aren't close enough to farm fields to make this practical. The sheer expense of shipping manure, which is high in water content, generally prohibits this. To compound this problem, CAFO material is frequently high in harmful bacteria, animal antibiotics, and pesticide residues. Having been underbid by synthetic and organic nitrogen and sidelined by consumed pesticides, CAFO manures sit idly by while their rich nutrients are evaporated into the atmosphere or leach into nearby water systems. That's the end of chapter 6. Thank you so much for listening. If you would please like and subscribe to this channel and this video. That way you'll get notifications when the next chapter comes out. If you're interested in learning more about the background of this chapter, some of the research that I did, I'll be sharing that on my Patreon page. You can look into the notes below and find that and head on over there if you would like to have some more in-depth information. Thank you so much for listening. Bye.